Well, welcome back, everyone. Looks like it's time to start. I did have an issue today before starting today's class. For some reason, the classroom that I normally teach from is not available. There's something going on with the STEM Academy of some sort, and the faculty to support office is closed right now at 5 o'clock on the Idaho Falls campus. So my last resort was just to run back to my office where I am now to teach here instead. So sorry about that. The classroom was not available. This desktop that I'm teaching from in my work office doesn't have a web camera attached to it. I should probably bring one, but we'll still get through today. It's a similar setup. It's just going to feel a little bit different on my end. But aside from that announcement, we'll still make class happen. Where we're at currently is on the last problem of section 4.4, L'Hopital's rule, and we'll then move into section 4.7 on optimization. Also, the next bigger announcement is that the information for exam 3 is now posted. The sections are going to go from 3.8 up to 4.7. It's going to be about the same length. It's going to come to 9 questions in total. So similar length from exam 2, exam 1, and same rules as well for this particular exam. So 1 page of notes, a scientific calculator, and if you'd like, the sample exam 3 problems are also posted here. As before, probably best way to be prepared is just get fully caught up on the homework sets up to section 4.7. I'll be grading them as fast as I can, as fast as I can get them. After that, start putting together your page of notes. You can have anything whatsoever on these notes, formulas, examples, anything that you think is going to help you get through the third exam. And it'll be set up to run just pretty much identical to exam number 2. I'll send out an announcement tomorrow morning on how to schedule your exam, but pretty much it's just going to be the same message that I send through Canvas with exam 2's changed to exam 3. They'll be open to be scheduled between the dates of the 27th of July through the 30th of July. So same for exam 1 through 2 for those 4-day block. But aside from that, again, sorry about the weird setup today. I probably sound different. Camera is not attached to this computer, but we'll still do the best we can. Any questions or comments at all then before we start today? Okay, well, we left exactly one problem at L'Hopital's rule dealing with indeterminate forms, but let's take some time to kind of refresh and warm up before just diving into that problem. Here's the statement of L'Hopital's rule altogether. Let me see if I can get this to zoom. Give me a moment. Let me just break this up. Okay, so above is the statement of L'Hopital's rule. If we have an indeterminate form of type 0 over 0, or an indeterminate form of type infinity over infinity, so those two indeterminate forms down below, then the value of the limit is truly just indeterminate. It could come out as anything, 0, infinity, some other finite number. The idea of L'Hopital's rule is we look at the rates that the numerator and denominator are heading towards 0 over 0, or possibly infinity over infinity, then it's the rate at which they head towards those quantities that's truly important in the limit. So we take the derivative, which tells us the rate at which something is heading towards 0 or infinity, same for the denominator, as x tends to a value. And if this limit exists, it's the same exact value as the original limit. So that's the major idea with L'Hopital's rule. It extends what we know about limits that we dealt with in chapter 2, whether the limit's going to a finite number or going to infinity, like in part E. And it's stuff that will come back in a Calculus 2 setting as well as in Calculus 3. There'll be situations where L'Hopital's rule just comes up. So that's the refresher on L'Hopital's rule. We'll apply it on this example down below, x to the power of 1 divided by x, which is a pretty bizarre function when you think about it. Any questions or comments before we get started? Okay, so the essence of L'Hopital's rule is pretty much taking these derivatives. Like we mentioned here in this purple arrow, we're not using the quotient rule. We're treating the numerator and denominator as independent functions. The thing that is rough about L'Hopital's rule is that these are the two indeterminate forms it works on, but there's other indeterminate forms that come up. And this is one of those other forms. If x is heading towards infinity, there's really two component functions we're looking into here. There's the base function, base x. Let me fix my markers real fast here. And then there's the exponent function, 1 to the power of x. So there's our two functions. X is heading off to infinity. So let's do the preliminary analysis of what happens here. As x tends towards infinity, we have that it's redundant, but this is one component of the base. X tends towards infinity. And here's the exponent, 1 over x. Well, if x is getting large and large without bound, then 1 divided by x is just approaching 0. So if that's the case, the form that we have here is indeterminate. Type, our base is going off to infinity. The exponent is going off to 0. And now pretty much anything can happen here. The result could be infinity. The result could be 1 using exponent laws. A base a to the power 0 is 1, but that doesn't always work if it's infinity. So we're looking at that indeterminate form there, infinity to a power 0. So we can't differentiate this as it stands. We need to do something to this function so that it becomes either a 0 over a 0 or infinity over infinity, either positive or negative. But now we know it's indeterminate. We can't just analyze this and get a number out. We need to do further work on x to the power of 1 over x. So that's going to be our next steps. Any questions with the initial analysis on this one? Okay. Well, we have a kind of a nice algebraic trick that's going to come up whenever a weird exponent situation like this occurs. I think this is going to happen on one of the problems in the homework, possibly the last one as well. So this is a good trick to come back to. If you have, let's just write down as a generic formula, a to power b is something that comes up. If you ever need to move around the exponent b, you can make that happen. You can rewrite this as, let's say, e to the power of the natural log of a to the power b. It got really complicated, but that's a bona fide step to take because if we chose to cancel, properties of logarithms say that's a cancellation right there. You just get a to the power b. But now another property of logarithms say that this power can move in front of the logarithm, and so this could be rewritten as e to the power of b times the natural log of a. And so that's the idea. If you need to move that exponent b some way, somehow, there's a trade-off. You have introduced the base e exponential function, and now there's a natural log in there, but there it is. B has moved. So if we're trying to get to a 0 over a 0 or an infinity over infinity, we need to move that exponent, and this is the major idea that gets us started. So now we're ready to start the limit. So this is the indeterminate form analysis. Here's our algebraic trick. And our limit using that trick becomes limit as x goes to infinity of e to the power natural log x to the power of 1 over x. Now we can move that exponent down. It's going to multiply natural log x, and so it'll look like this. Limit as x tends towards infinity of e to the power 1 over x times the natural log of x. And we have yet another trick. E is a continuous function, and when we're using continuity, a limit can transfer inside that function. That's a trick that we looked into way back in section 2.5. So if we're taking the limit of the base e exponential of anything involving a function x here, We could rewrite that as e to the power of the limit as x tends towards infinity. Let me rewrite this as natural log x divided by x. So we started with the limit, which is kind of complicated to look at, but it's indeterminate. We can't do much with it. Now it's a little bit worse. The limit is in the exponent position, but the trade-off might have been worth it. We have x in a denominator, a 1 over x really. We have a natural log x in the numerator. Let's do another analysis of this as an indeterminate form. It looks like it's going to be infinity over infinity. So the analysis says as x gets larger and larger without bound, as x tends towards infinity, the numerator, natural log x, it also tends towards infinity, just very, very slowly. And the denominator, x, let me redo my highlighting. I want to visualize it as just x, an independent function, rather than a 1 over x. X is also going to head towards infinity. So this is cause for celebration, right? Right when we get to this stage, either a 0 over a 0 or an infinity over infinity says this is indeterminate. I'll use IND, the shorthand here for indeterminate, type infinity over infinity, which means L'Hopital's rule applies to that limit. It didn't apply to the original one, so we did this algebraic backflip to get it to this applicable stage here. Now we just take the derivative of the numerator, divide by the derivative of the denominator, and we're about done with this one. Any questions to this stage, analyzing this bizarro function? Okay, here's the next step. Like we did earlier in the notes, now that I'm about to use L'Hopital's rule, I often notate that by putting an H above the equality to say, this is the actual L'Hopital's rule step. Everything above was just algebra. This is e to the power of a limit as x tends towards infinity. We differentiate the natural log x. That will give us a 1 over x. Divide by, take the derivative of the denominator, which is just x, so we get 1. And that's the whole use of L'Hopital's rule there. There's nothing further to say other than to simplify and take the limit. So that's what's being conveyed. Whatever your numerator function is, take that derivative, divide by the derivative of whatever the denominator function is. Note we didn't take the derivative of natural log x over x as one whole function. We treated the top and bottom as independent functions. Here's what we got. And now this is e to the power of the limit as x tends towards infinity. This just simplifies to 1 over x. And we've seen this limit. As x tends towards infinity, 1 over x tends towards 0. So this just becomes e to the power of 0, which means the entire limit is exactly 1. And then that ends this problem right here. So if x was 5, this would be 5 to the power of the 5th root. So 5th root of 5. If it was 10, it would have been the 10th root of 10 and so on. What this is saying is as x gets larger and larger, that number x, take the xth root of that number, and these values are just going to get closer and closer to a value 1. Well, that concludes our last L'Hopital rule problem, the entire L'Hopital rule section. What we're going to do is skip next to section 4.7 on optimization, another major application of the derivative. But any questions or comments at all getting through this last problem here? Okay, let me save this up. Now let's take a look into that next section. For that next section, the major idea is really it's a decent review of section 4.3. where we're looking into the first derivative test for local minimums, local maximums, and the second derivative test for local minimums and maximums. The only slight change is we have fine tuning on both the first derivative test and the second derivative test so that we can find the absolute maximums and the absolute minimums. So we're going to start off with a second derivative test. This is one of the tests that we used last in section 4.3. Then take a look into the first derivative test. But look at what we're trying to achieve here. We're going for an absolute minimum and an absolute maximum. So here's the rundown for the second derivative test. We have a second derivative that's continuous near a number c. That number c is going to be the critical number, which means the derivative of f at c is 0. And it says something about a local minimum, a local maximum, but we're going to apply it after the moreover statement. We're going for an absolute maximum or an absolute minimum in the problem. If the second derivative is positive for all x in the domain, then we have an absolute minimum. So we're not saying positive at the critical number. We want always positive, no matter what. Likewise, if the second derivative, if we can show that it's always a negative number, no matter what you put inside there, second derivative is guaranteed to be negative as a function, then once we find the critical number, f at c is an absolute maximum. So this is the fine-tuning adjustment right here. Right where it says for all x, we want positive and negative for all x. If you can make that happen, you have found the absolute maximum, absolute minimum. Aside from that, this test works very similar to how we applied it in the last section. And example 1 doesn't have a whole lot going on with it. In fact, I think some people, when they see this problem, they probably can already guess the answer to it. But the reason we're starting with kind of a simpler problem is really to focus on the test. Not too much going on with the example right now. Our examples are going to grow in complexity as we go from examples 1 through 4. But this is a good one to just get it started. Any questions at all, folks, before we give this one a try? Okay. Well, it says the sum of two positive numbers comes out to 15. We want to know the smallest possible value of their sum of cubes. Again, think of this one as kind of a warm-up problem. I think there's a similar one to this one assigned in the homework. From the first sentence, when it says the sum of two positive numbers is 15, our problem-solving strategy would tell us we should indicate variables and write down an equation that captures that first sentence. So let's say let x be bigger than 0 and y be bigger than 0 satisfy their sum, x plus y, is 15. So that's sentence number 1. This one should have had a question mark. Let's fix this. What is the smallest possible value of their sum of cubes? There's that question mark that just feels a little bit more grammatical. So we want to minimize if they're asking about the smallest possible value. Minimize this function. It's the sum, but of their cubes. So x cubed plus y cubed. So that's the function we would like to minimize. And we can even give it function notation. We could call this f of x equals x cubed plus y cubed. The moment we do that, though, we might spot a problem here. There's function of x that we're dealing with. The right-hand side has two variables, however. Y is a function of x, and we need to put that explicit function on this one. In order to use these tools right here, we need really one function involving one single variable. But it's not too bad to do since this is really a constraint equation. We can solve for the variable y here, plug it back in, and we'll have a function of just x alone. So let's make that swap happen. You can solve for either x or y, but if you indicate this as a f of x, solve it for y, we have y equals 15 minus x. Grab that value for y, substitute it here. F of x is now equal to x cubed plus 15 minus x to the power 3. So that's the function that we want to minimize, and we'll do it through the second derivative test. So that's a good amount of the analysis already, even though the context it had just 2 sentences. This is pretty much what we're going to do in a lot of these problems. Sometimes the problems give us the function right where the red dot is, but in other half of the problems, we have to build up to it like we just did for this one. Any questions at all to this stage? Okay, and this is actually a great place to be. Once we are right here where the red dot is, it becomes a section 4.3 problem. We're just going to do the calculus just like we did for second derivative test with this small adjustment. First step is differentiate the function. Let's call this step 1, as in step 1 for the second derivative test. I'm going to differentiate it using the chain rule because the chain rule is a lot less algebra than, or calculus, than dealing with expanding 15 minus x to power 3. That's quite a bit of algebra. So let's go left to right. Derivative of x cubed is 3x squared plus chain rule on this one will give us a plus 3 to power 2. Chain on a new derivative and drop in the inner function 15 minus x. So that's our first derivative so far. We need to solve the first derivative set equal to 0. So we need to simplify this as much as possible and get to that stage. So at this line, this is going to be 3x squared. The derivative of this is just going to be 0 minus 1, so negative 1. Negative 1 is going to multiply this 3, so it becomes negative 3. And now it's a good idea to expand all this. So let's maybe do that on another line so we're not cramming a bunch of steps into one single line. Let's expand this as much as possible just to make the equation solving, setting it equal to 0, a little bit more manageable. So next line, it's 3x squared minus 3 times. Let's maybe do the expansion over here on the margin. 15 minus x squared is just 15 minus x times 15 minus x. And the numbers are getting a little bit hairy on this one, so let me make sure I remember 15 squared. I think that's 225. Yeah, 225 for 15 by 15. Then we'll get minus 15x plus x squared. So altogether, simplifying that, we're looking at 225 minus 30x plus x squared. Now, we need to distribute in negative 3. Good amount of algebra in this one. 3x squared. 225 times 3 comes out as a 675. So we'll get a negative 675, distributing that negative 3, plus 90x minus 3x squared. This is kind of a nice algebraic accident that power 2 has dropped out. And so the complexity of solving this equation has gone way down. We don't have to factor it this time. Now we're just looking at 90x minus 675. So that's our first derivative. And we're still in step 1. We want the critical number, so we set this equal to 0 and solve. So here's the yellow highlighting. Here's f prime at x all the way at the bottom, following that chain of inequalities. It's set to 0. And this will imply x equals 675 over 90. And we're almost there, 675 over 90 comes out as a 7.5. So x equals 7.5 is the critical number of f. So we've got a critical number down. That means step 1 is complete. We're ready to go to the next step. Any questions before we take a look into the next step? Okay, here's where it gets pretty tricky as a homework problem. In the homework, I try to put extra guidance in section 4.7 about the expectation of steps you'd have to do for this one. That's not the homework. Let me try again. 4.7 assignment. There it is. It says state the name of the chosen test so I know that you know which test you're using. Show all steps of the test. We'll know we need to show conclusion, but that part's pretty tricky all on its own, showing all steps of the chosen test. The easy mistake to make is once we get a critical number, if x is 7.5, y is 7.5, then we can just sum their cubes, feels like we're done. But the reason this test is so big is lots of weird things can happen when we're finding maximums and minimums. Let's go back to section 4.1 for just a moment and take a look at one particularly nasty function. So we were just talking about minimums, maximums, local mins, local maximums. We were introducing the idea of a critical number through Fermat's theorem. We just solved for our problem, f prime at c equals 0, and got 7.5 as the critical number. But you know, that's not always the whole story to these kinds of functions. Sometimes a critical number could lead to an absolute minimum. Sometimes it could be an absolute maximum. And other times it might be neither. So in this function, we differentiated it, we set it to 0, we found the critical number is 0. So even though f prime at 0 is 0, this function doesn't have a maximum or minimum at all. So this one was really kind of surprising in this context of where we're at now. Just because we have a critical number doesn't mean we're done. Anything can happen, depends on the original function. Here it is in this form. So we have to actually prove that the critical number is going to lead to an absolute minimum, which means we're going on to the second stage of the test. So here's step 2. This is required for full credit. It's a massively important step. These problems are 15 points altogether. And for a lot of these problems, this would be a 5-point step right here. So step 2 on the second derivative test, we're now proving the critical number is actually going to lead to a minimum. We need to take the second derivative and show that no matter what, this second derivative is positive. That's all it takes to prove we have an absolute minimum. So it's a powerful, powerful test in how fast it is. So we have f prime at x right here in its most simplified form for differentiating. Now f double prime, let me keep it, let's keep it blue to match the color coding here. F double prime at x is negative 675. Or hang on, let me try again. That would go to 0 when we differentiate. The derivative of this would give us just 90. Not sure why I fixated on that constant. So the derivative of this is 90, constant goes to 0. And when we look at that, the second derivative is just a constant function. It's trivially true that this is absolutely greater than 0 for all x. This has to be all x in the domain of the function, but the domain of function was just positive values for x. So we can say for all x greater than 0. But once you have that, if f double prime is positive for all x greater than 0, we've proven we have an absolute minimum. All we need to do is find the smallest possible value for their sum of cubes. So we're on to the last step. So this proves there is an absolute, we'll use ABS for absolute minimum. Now here's Step 3, just showing our conclusion. Well, any last questions at all, folks? Actually using the second derivative test here on step 2? Okay, well, let's give the conclusion now. We can't stop by just saying a critical number and saying there is an absolute minimum. We have to answer the direct question posed in the problem. Smallest possible value of their sum of cubes. Well, f of x here is the sum of cubes. And in the conclusion here, f of c is that absolute minimum. So let's keep it in blue to match that color coding. We can now say, therefore, f at, take the critical number 7.5. If we do that, we'd be cubing 7.5 plus 15 minus 7.5. That's just another 7.5 once again. This, whatever it comes out as, is the absolute minimum sum of cubes for this particular problem. Let's find out what that comes out as. 7.5 cubed plus 7.5 cubed is 843.75. So we'll say that that is the absolute min by the second derivative test. And now our work is complete on this one. We'll try more involved contexts, but this is a good one to just start off as kind of a warm-up problem. Again, some people might know the answer to this. If you have two numbers summing to 15, the short method was just divide 15 by 2, and that's where the 7.5 is really coming from in both of these spots. Well, we'll look into different problems, different contexts, but any last questions or thoughts getting through the first one? Okay, well, here's what we have going on for the next ones. Next one, we're going to take a look into a fine-tuned first derivative test for extreme values. This one is going to look like it's about marine biology. We're looking at a rate of photosynthesis for phytoplankton given by that function. Next, this one looks like it has something to do with business. We're going to try to optimize the cost of materials for some interesting container that has these design choices and cost of materials. And this will be our last example for the day. This one looks like it's biology. We're going to look into how a fish minimizes its energy expenditure depending on the length that it has to migrate to some new habitat. And there's a bonus problem here. This one is more to just to show the power of the optimization methods. We won't solve this one in class. This one does get pretty involved, but our optimization techniques are also powerful enough to derive Snell's law for physics that shows when light shines through water, it causes this distortion effect because it's minimizing the time it would have to travel to get from a point A to a point B. If you're curious about the solution on this one, let me know and I'll be very happy to post the solution to Snell's law. This one goes beyond what's actually in the homework, what we could ask on an exam. So again, it's just for fun to show some of the powerful methods in the sciences, physics, that these can be applied to. But let's start up on the very top. We're going to go back to this photosynthesis function. And here's our first derivative test. We should analyze the test first before we just jump in. It's slightly adjusted for extreme values. It says, to start off, suppose C is a critical number of differential function defined on an interval. What we're saying here is f prime at C equals 0. That same equation we saw in section 4.1. Now it says if f prime at x is positive for all x less than the critical number and negative for all x bigger than the critical number, then f of c is an absolute maximum of the function. Taking another look at that, if you insist, let me space this out just a bit. If you insist that the derivative is positive for all x smaller than the critical number, it just means it's increasing up to the critical number. The derivative is 0 at the critical number, so it's neither increasing or decreasing there. But we have to watch out for these functions. Sometimes functions are increasing, they hit a critical number where the derivative is 0, and then they continue to increase again. So the second part of part A says, and if f prime at x is less than 0, meaning decreasing in this case, for all x bigger than the critical number, then you have an absolute maximum of the function. So that means this bends down and you had an absolute maximum. So we're trying to eliminate this possibility by carefully analyzing these two conditions relative to where you are at for the critical number. The other one just says if it's less than 0, so decreasing, for all x less than the critical number, bigger than 0, so increasing, for all x bigger than the critical number, then you have an absolute minimum in that case. So that's the first derivative test in a nutshell. Really, it's the same test from section 4.3. There's not much of an adjustment other than what's really going on with condition A and B is there's exactly one critical number, and it goes from increasing to decreasing or decreasing to increasing. So if you have these features, there is not just a local min, local max, like in section 4.3, but an honest absolute maximum or absolute minimum. So putting these ideas together, we'll run through the first derivative test on this example too. And we'll also see why we like the second derivative test. It is quite a bit faster, less analysis, provided that taking the second derivative is fast. Any questions at all before we begin? Okay, so we're looking at a pretty complicated unit. The rate in milligrams of carbon per cubic meter. This is for phytoplankton, so we're thinking of an area of these organisms. So milligrams of carbon per cubic meter per hour at which photosynthesis takes place for these phytoplankton can be modeled by this function, 100I divided by I squared plus I plus 4. I is light intensity. Another interesting unit, this light intensity is not in lumens, it's measured this time in thousands of foot candles. So interesting unit there. And we want to know for what light intensity is P a maximum. We can think about the function in this way. If I is light intensity, it's like the variable x in the function, and it would have a minimum this time. We would say I is greater than or equal to 0. 0 means absolute darkness, and the light just gets brighter and brighter. But if you're trying to grow these phytoplankton to make photosynthesis take place as fast as possible, and that's your function, you can imagine at 0, that's not fast as possible. Your phytoplankton are just dying. So you start to turn on the lights higher and higher, and photosynthesis is going to get better and better as light intensity increases. But there's going to be a turning point, right? There's going to be a point at which the lights are so bright, you're just cooking the organisms. They're just frying in the water. So we want to know at what point is the light increasing the rate of photosynthesis, and at what point is it starting to decrease? The phytoplankton are now being killed off, essentially. It's too much brightness. We can find that optimal point, then we can maximize the growth rate in terms of measuring photosynthesis for that particular species. So that's the idea behind this problem. So P for photosynthesis, I for light intensity. I is the independent variable. So think of it like a variable x if you were to differentiate. If you were to differentiate this, you can think of it in terms of quotient rule, where that's the numerator, that's the denominator. And essentially, that's the first step on this. If we want to use the first derivative test to maximize something, we solve the critical number. So that means we need the derivative. I'll do this one in Leibniz notation, dp di. So that gets us started. Now, quotient rule on this one, if it was 100x, that would just be 100. That variable I looks a little bit weird, but same exact idea. The derivative of 100i with respect to I is just 100. Then we multiply that by I squared plus I plus 4. Go subtract in quotient rule, copy the numerator, 100i. Then multiply that by the derivative of the denominator. This denominator will have derivative 2i plus 1. Finally, all of it's divided by I squared plus I plus 4 squared. So we're on our way. We took the derivative. We still need to simplify it, solve the derivative set to 0 to get the critical number. But one thing to note about this problem is it's kind of nice in the way that they just gave us the function, unlike example 1, where we had to build our own function. In some problems, you're just ready to go. If you have a function provided, we just start right at the derivative. Any questions at all computing this derivative? Okay, let's take the exciting work. We practiced this in chapter 3 of just simplifying it. First, distribute 100 into the group. We have 100i squared plus 100i plus 400. Distribute negative 100i. This will give us minus 200i squared minus 100i all over that denominator. I squared plus I plus 4. I have to admit, I is not my favorite variable to write. The penmanship can go sideways sometimes. So let's see what we have here. 100i is going to bounce with minus 100i, so we have a quick cancellation going this way. Then, altogether, we'll have 400. 100i minus 200i gives us minus 100i squared, rather, minus 200i squared. Gives us negative 100i squared all over I squared plus I plus 4 squared. And we see a situation kind of like this in section 4.3. The numerator factors, we can factor out 100. That's going to leave 4 minus I squared over the I squared plus I plus 4. And then we continue to factor. This factors as a difference of squares, the 4 minus I squared. So now we're at 100. 2 plus I, 2 minus I, all divided by that I squared plus I plus 4, which has just been coming along for the ride. So there's the derivative. dp di is equal to all of that. Next step is, because we want critical numbers, we set that equal to 0. But algebraically, the only possible way we get 0 here is if the numerator goes to 0, and that gives us the critical numbers right exactly at this step. This implies I equals, well, it can't be negative 2, because I is the light intensity. There's no sense to having a negative 2,000-foot candles. It starts at 0 and just goes up. So we only get one solution. I is 2 in thousands of foot candles. Let's put a quick note here. I cannot equal negative 2, so we lose that particular solution. But that's what we're expecting for these kind of problems, because if we're going for an absolute max or an absolute min, remember we expected exactly one critical number, and that's what we found. I is 2. If we have multiple critical numbers, it's probably a domain issue. So check the domain of the function. or maybe an algebraic mistake. So if the domain of the function doesn't eliminate one, double check your derivative, the simplification, and so on. Well, the rest of it is just ordinary first derivative test. We want to show that it's increasing to the left of 2, decreasing to the right of 2. And if we can do that, we'll be able to find the light intensity that makes P a maximum. So that's our question right there. For what light intensity is P a maximum? Any questions before we go to that next step? Okay, well, this is step 1 and first derivative test, get the critical number. Next, step 2. It's good to remind ourselves because this is worth a lot of credit in step 2. Make sure you show this somewhere in your analysis because we're trying to eliminate this possibility. Maybe the function is just messed up and the light intensity on the critical number, it keeps increasing. That doesn't seem realistic to the context. But if the function is just not a good function that models photosynthesis rate, that absolutely could happen. So we're looking to show once and for all through the first derivative test, I equals 2 gives the actual light intensity for a maximum. So this is what we did in section 4.3. We wrote down a number line. It went from negative infinity to positive infinity, but this time it's an I interval and it starts at 0. So we'll draw a number line that goes like this. I is light intensity. Critical number is at 2,000-foot candles. Now we want to know the sign of the derivative on those two intervals. So the next thing we always did in section 4.3 is take test points. So this looks like a good color for test points. We can test a value in this region, say a value 1, compute dp di when I equals 1. We just want to know the sign of the derivative. If it's positive or negative, we're plugging 1 here. That gives us 100, 3 times 3 times 1. In the denominator, it's 6 squared. When we plug in a 1, and we never really computed the whole number in a lot of cases. We're just looking at the sign. It's obvious, absolutely is the word I'm going for there. It's absolutely a positive number. Just multiple values positive being divided by a positive. So you can either call this P prime at 1, or I'm sticking to Leibniz notation on this one, so I went with dp di. That means here, dp di is positive, but that just means P, photosynthesis itself, is increasing. So I'll write P increasing just as a reminder. Now, if we have the right critical number and the model is a good one that they gave us, we take the value to the right of 2, any convenient value whatsoever, whether it's 10, I'll go for a 3, we're hopefully getting a negative derivative. So dp di, evaluate when I equals 3, comes out as, here's the derivative, 100 times 5 times negative 1. The denominator is positive no matter what. It's 9 plus 3 plus 4 squared. This means the whole thing altogether is negative, thanks to that one negative sign, less than 0, which finally, in the logic of the first derivative test, this entire interval is negative, less than 0, which means the original function, P, the rate of photosynthesis, is decreasing. So if we go beyond 2,000 foot candles, these particular species of phytoplankton are not happy. They begin to produce less and less photosynthesis. So we're just about there. We just need to put down a conclusion. So here's the final step, pretty much mirroring the same 3-step process where we're emphasizing the necessity of step 2 more than anything. Any questions at all with the interval analysis? Okay. Also, notice what's being asked this time. In the last question, they were asking what was the smallest possible value of the sum of cubes. We had to take the critical number, put it inside the function, and get the output. This one's different. It doesn't want the output. It's talking about the doesn't want the output. It wants the input, the light intensity, to answer the question. So we can end this one a little bit more fast and just say by the first derivative test, I equals 2,000-foot candles maximizes P, the rate of photosynthesis. And that's our overall conclusion. We have a statement of the maximum, we have a statement of where it occurs, and we have to say what test we used as well. So that's the complete rundown of the first derivative test. Second derivative test, the second step usually goes really, really fast, but that only will work if taking the second derivative goes really, really fast. And taking the second derivative for this one, that's not the case. I think if you went to take the second derivative and simplified it as much as possible, you also have to come up with a ironclad argument to show why the second derivative is also negative. And that can be sometimes more work than taking the second derivative. That can be a lot of work to show something is always negative if your function is very complicated. So the more complicated your function looks, the harder it is to differentiate, the better the first derivative test becomes. Doesn't mean the second derivative test is bad. It has plenty of use cases, but you just have to be careful with which function you're actually going to use it on. Well, we're going to try out another one just to see how it goes, get some extra practice. We have 2 more for these notes. Any last questions or thoughts before we try out the next? Okay, well, here's our next adventure. The context is now shifting to economics. This one has a lot of moving parts. And the idea with this one is it's a bit of a geometry problem too. Problem solving strategy here is sometimes you have to build your function, just like we did on example 1. But if a picture helps because lots going on with geometry, it's absolutely a good idea to draw a picture. So we're told that we have a rectangular storage container with an open top. We take that to mean that there's no top involved in the construction of this. It is to have a volume of 10 cubic meters. I have no idea what we would do with this. Maybe it's something to be used in farming, who knows? The length of the base is twice the width, so somehow that's an important specification. And the material for the base is $10 per square meter, which is dirt cheap. So again, it's kind of hard to imagine who we're building this for, but let's just keep on following the logic. Material for the sides costs even less, $6 per square meter. Again, really, really cheap, probably a flimsy material. It's got to have 10 cubic meters of volume. And we're trying to find the right length and width for the cheapest such container. It's cheap already, but maybe we're doing a lot of these and we want to build this as cheaply as possible. So a lot going on with this context. Let's start over reading through it by first drawing a diagram that conveys that information. Rectangular storage, we're not considering the top, it's not part of the construction, and the length is twice the width. So you don't have to be an artist for this. It can be a pretty crude diagram. It's going to be pretty crude because I'm certainly not an artist. I'm going to draw 2 squares. This is usually how I get a rectangle going, 3-dimensional. Just kind of connect the dots. I sort of missed on that one, so we'll use our imagination where we need to. Connects like that, and this is harder than I remembered. This is a edge that you wouldn't see as the right side comes around. then it comes through like this. And that'll do the job. There's our rough diagram for the rectangular storage container. So if you ever have to draw this on exam, here's the strategy. Put down two squares and just connect line segments. Here's the next piece of information. The length of the base is twice the width. So I'll call this the width, this the length, because it looks longer, and that's the height. Now we have material costs for everything, but let's focus on the volume for the moment, which is supposed to be 10 cubic meters. And maybe before even that, let's look at this sentence again. When we said the length is twice the width, what we could do is call the width x. Then the length becomes twice x. So now we've conveyed this sentence down using that algebraic structure. So there's an x, there's a 2x, and by a similar token, we can call the height a y, just an easier variable to write down. You can leave it h. You can make this 2w if you prefer L, W, and h. But I think x's and y's are kind of comfortable, a little bit easier to write down. So there's our rectangular storage container. We have a requirement on volume, 10 cubic meters. So we can start by writing volume is 10 meters cubed. But from this statement, we also have some algebra that we can write down based off that information. Volume of a cube is just the width times the length times the height. So we can say width, length, height is 10. We can substitute in our particular variables. X times 2x times y is 10. So 2x squared y is 10. So everything up to this line highlighted there gives us that equation. 2x squared y is 10, where the meaning of x and y is through this diagram here. Now we're ready for material costs. So that's going to be our next thing to take a look into. Any questions to this stage of the analysis? Okay, I think this is pretty tricky because we have several different kinds of sides that we have to take into account. We have the left side, the right side, the front side, the back side, and the base. Again, we're not considering the top, it's just missing here. So probably a good way, if we're going to find the cost of the cheapest such container, let's just go side by side and find the individual costs. So to start off, let's say cost of the base. Let me put a temporary highlighting here to show which side I'm looking at. So there's the base with the squiggly line. The cost of the base is going to be, first, the area. We would take x times 2x. We write it this way, area times the cost for the base, $10 per square meter. So that'd be area in square meters times $10 per square meter. Now we can substitute in what the area is for this one. Area for the base would just be x times 2x times 10, divided by meter squared would cancel, and this is now in dollars. So in dollars, this would be 20x squared. So that's our base cost. We're now going to focus on the sides. And the sides, it's cheaper, $6 per square meter. But it's a little bit annoyed because there's a left-right side, there's a front-back side. So we can split those up as well. Idea is kind of divide and conquer with this one so that we don't try to do too many steps all at once. I would say it makes sense to look into front and back sides next. So we'll come back to the 20x squared. Now we're going to look into cost of front back, the front and back panels. This time there's two panels, so we have to double the area. It's going to be twice the area times the rate per square meter, $6 per square meter. So now we take the doubling factor because there's a front and a back. The area for this rectangle here, same as this area, is just going to be the length x times the height y. So 2 times x times y times 6. So altogether, this is just 12xy. So we're getting through this one. This one's looking like one of those longer problems. This is probably not a great problem for exam 3 since it's limited time. This one could work a little bit better on, say, the final exam, since those are a 2-hour exam. And something like this could come up in homework as well. So that's why we're getting through it here on the notes to help out. Well, we've got the front and back panel down. Next, we're going to look at the left side, that one, the right side, that one. So let's just call this cost of left and right sides. And same idea as what we did before. We want to take 2 times the area, since there's 2 panels. The rate is still $6 per meter square. So when we find the area, only difference this time is its length, 2x times y, so it's 2xy this time, times 6. So this is altogether 24xy. And we're finally there. We're looking into cost of materials. We have a cost of the base, cost of the front back panel, the left right sides. Forgot to put units on those. And so now we can say total cost. We can give that a new name, like say, let's go with C on this one. C equals total cost. And now as a function, C of x equals the 20x squared plus 12xy plus 24xy. So now C of x is 20x squared plus 36xy. We finally have a function. So really, even though the context is more involved, this is essentially the very first thing we were doing on example 1, when we finally got a function here for f of x. Just more things going on, a little bit more moving parts. If you add different areas, different rates of cost for materials, then the preliminary work seems to explode pretty fast on these kind of problems. Well, just like that last problem, we also have another issue. We have a function of x, but there's a y variable here. It's okay because the constraint of volume must be 10 cubic meters will allow us to solve for y. So we can come back here, divide by 2x squared, and y would be 5 over x squared. Substitute that in, and we have a cost function involving just the variable x. On the next line, C of x is 20x squared plus 36x times 5 over x squared. So we have C of x, finally, let me put it over here, is 20x squared. 36 times 5 sounds like 180, but let's be real sure here. So we get 180. X times x squared. Well, we have to differentiate this. So using the power rule, that's best simplified to x power -1, with base x in the numerator. And finally, that function c of x conveys all the information up to the last sentence, which is more of a demand. We want to minimize that cost function. So if you adjust the side length x, you also are adjusting the length L, but you have more independence here. You can also adjust the height y. Do that in a way you always get 10 cubic meters, and that conveys the cost no matter what adjustments you are going to make. We're trying to minimize it next, which means whether we're going to use the first derivative test or the second derivative test, we need to differentiate this and get a critical number. So here's after the preliminary analysis, here's step one. I mean, this is a big set of steps here, but here's where either first or second derivative test would start. That's the step one for those. Step one, you differentiate the function. So c prime at x would be 40x minus 180 x to the power negative 2. That's a fast derivative, which tells us the second derivative is possibly a good idea on this one. We need to set this equal to 0 and solve. So if you set that to 0, this would imply 40x is positive 180 x to the power of negative 2. This is really 180 divided by x squared. That's a decent way to convey this. Actually, let's write this down in the notes just to show that. This would be 40x is 180 over x squared. This kind of better conveys what you want to do next. Just multiply both sides by x squared. Or if you're a cross product type of person, you're just multiplying x squared across equality like that. You get 40x cubed is 180. Now let's take 180 divided by 40, or 18 divided by 4 equivalently. X cubed is now 4.5. We almost have the critical number. That's just the critical number to power 3. So take 4.5 to the power 1/3 to cube root it. And that's kind of an inconvenient number. I'll keep it in exact form for the moment and just say x is cube root of 4.5. So that number x, let me scroll down just a touch, is the critical number of c, our cost function. So now that we have a critical number, we're ready to start optimizing, proving critical number is going to lead to the cheapest container. Any questions before we hit this with the next step? Okay, on these kind of problems, it'll always be up to you if you want to use the first derivative test or the second derivative test. But I encourage you, work efficiently. Here, let's put down, just for the sake of notes, we will use second derivative test since c double prime is fast to compute. We also need to show c double prime is always going to be positive, so that's part of it. But this is a good indication you should try the second derivative test. If computing the next derivative is almost immediate, it's worth looking into. And here's how it goes. Just go to second derivative, c double prime, add x. We differentiate 40x, which is 40. And then we take 180 times 2, that's going to be plus 360, x to the power of negative 3. Now, in the second derivative test, if we're trying to find the cheapest such container, a minimum, we need to prove that this is always positive, no matter what. That's kind of problematic with what it looks like, because there are some values for x where 40 plus 360 x power negative 3 is truly negative. So if it seems to be going kind of awry, here's the next thing to look into. There is a domain condition on x. We never wrote it down. We probably should have when we wrote down this diagram. But if c is a cost function, c equals total cost, the domain is that x has to be bigger than 0. It shouldn't even be 0 as well. If it's 0, that means the width is 0, the length is 0, and whoever's doing this job is going to get fired at that point. It can't be negative. It has to be some non-negative value, bigger than 0. Now we come back here. If x is always positive, then 40 plus 360 x power negative 3, that's always positive as well. So we can say that this is always greater than 0 since x is bigger than 0. Second derivative test is tricky, so let's take a peek. If you said second derivative is positive, as we did, that means you have found an absolute minimum. The conclusions kind of run contrary in that sense. Negative second derivative means an absolute maximum instead. So back down to our problem. We have a positive second derivative, so that means we're ready for step 3. We're just going to give our conclusion. We should check, what does the problem want? The last problem just wanted the independent variable I for light intensity. This one wants the actual cost this time. So x equals cube root of 4.5 is a width in meters, but we need to plug that back into the function to get the dollar amount. So we do have a output that we're wanting this time rather than just the input. So watch for the wording of the instructions. Sometimes it emphasizes the input or the output. Here we're going for the output, so we can say the absolute min cost is the cost function at cube root of 4.5, which means we go back to that function right there, the original function. Take 20, we'll put this in the calculator, but let's write this out for the notes. 20 times 4.5 cube rooted would be 4.5 to the power 2/3. Then over here, plus 180. The cube root of 4.5 to the power negative 1, we can write that more easily for the calculator as 4.5 to the power of negative 1/3. So whatever the index is for the root, it's the denominator in the exponential notation. And at this stage, we have a cost. Take 20, 4.5 power 2/3. We're up to $54, but that's not the whole story. So plus 180, 4.5 to the power negative 1/3. And this 10 cubic meter mystery structure comes out to $163.54. Rounding to the nearest cent is the normal thing to do with money problem. And we finally have that as the absolute minimum. So hardest thing to do about this problem is to try to come up with who is this for, what they're doing with it. But if you have a client paying you money to do this kind of analysis, this is what you would tell them the minimum cost would come out as. So this one, again, is a pretty big problem because it had a lot going on. Just to build the function, we'd have painstakingly put together all the information. It's very similar to example 1, but you can see with these kind of problems, the more you put into it, the more adjustments that you put into these kind of problems, the bigger and bigger they get. Well, we're going to do one more problem to call it a day. One last problem for section 4.7, going to a biology context. But any last thoughts or comments on getting through this one? Okay, well, here's the last one for the day. And hopefully tomorrow I'll be in my usual classroom. This is, again, kind of weird to teach from the offices. Hopefully I don't have a neighbor that's here today because these walls are really thin and probably pretty distracting. And here's how this one goes. It says, for a fish swimming at a speed v. So imagine a salmon or a trout. That's how fast it's going to swim relative to the water. The energy expenditure per unit time is proportional to v cubed. So we have v cubed here, a times L divided by V minus U. So a pretty complicated proportionality constant. But it looks like the first sentence is just setting the context. E is going to be energy expenditure, and V is velocity of the fish. Now, here's a concept from biology that says it is believed that fish migrate. Let me start again. It is believed that migrating fish try to minimize the total energy required to swim a fixed distance. And that makes sense. The more they can optimize the energy, the higher likelihood of survival, passing on their genes, and so on. So that's a reasonable statement to think about. Doesn't seem to tell us a whole lot, but the fixed distance looks like it's going to be L. So that's the role in the function that's been built for us. It goes on to say next, if the fish are swimming against a current U, now it's getting more complicated. V is how fast the fish swims relative to the current, but U is the speed of the current. That's why we have the fish speed minus the speed of the current in the denominator there, where U is less than V. That makes sense. This is saying the fish is swimming faster than the current. They're not being washed away down the Snake River, for example. So that's a reasonable assumption. So if it's swimming against a current at speed U, where U is less than V, then the time required to swim a distance L, that's in our numerator, is L divided by V minus U. Looks like A is the proportionality constant, and this is just the time required, part of the energy function. Total energy required to swim the distance, that fixed distance L, is given by that function there. A is the proportionality constant. I guess I should have read that far. It just tells us that. One assumption here is that we need, if it's the proportionality constant, we can assume that A is a positive value as a constant. We want to determine the value of the velocity that minimizes energy expenditure, which would be an amazing thing if we could do that. Just change the speed of the current to U. It'll tell us what V should be, and then we can measure that in reality. We could look at the average speed of a particular river and see how fast the fish are swimming to see just how well this model performs. So we're going to see what is going to minimize energy. Well, there's lots of constants, lots of stuff going on. So let's kind of do a inventory of everything we have here. V is the variable. That's kind of indicated well when it says E of V. So V is like X. A is a constant, we said before, but let's say it again. A is constant. It's positive, so we'll use the constant multiple rule when we differentiate. L is going to be the distance the fish swims, so L is constant. Also, we can assume L is a positive constant as well. U is the speed of the current, but when we say E of V, only the velocity, speed of the fish is changing. U, we're going to assume is constant as well. U is constant. And we can make a really big assumption here. U should be bigger than 0. The speed of the current should be not 0. It should be, that could be the case, but I think in the spirit of this problem, it's the current is moving, so bigger than 0. And also from this statement, the fish is moving faster than the current. So we have a triple side inequality. U is 0 is less than U, which is less than V. So a whole bunch of constants here, but the thing that's actually a variable is v itself. If we were about to differentiate that, it's probably not the best form for the derivative. That looks like it's a product rule, but with v in a denominator, there's more going on. We can rewrite the whole function as e of v is really al times v cubed divided by v minus u. So think of v as the variable x when we differentiate. It's going to play that role. A times L, that's just a constant, like the number 10. And U, lowercase u, is also constant, say a number like pi, for so on. So when we go to differentiate, we'll use the differentiation rules that takes those ideas into account, that those are all just constant. And that gets us started. That's our function. We can certainly differentiate this. We'll use the quotient rule and begin by saying e prime at v. If we're going to differentiate that, it's a tough one to visualize unless we're thinking in terms of what are the constants. If a and l are just a constant there, we can use the constant multiple rule that says al stays exactly where it is. Then we differentiate v cubed, that'll be times 3 v squared. So we're using the quotient rule. First step was to differentiate the numerator, then multiply by the denominator, v minus u. Then go minus, copy the numerator, alv cubed, multiply it by the derivative of the denominator. Well, the derivative of v is 1, and that's a constant that's being subtracted off, so its derivative goes to 0. This is just times 1, and that's the whole story. Then the whole denominator is just risen to a power 2, v minus u squared. So that's the whole derivative. Any questions or comments getting that numerator put down? Okay, next thing we always want to do is simplify that numerator as much as possible. So that would amount to, let's distribute al 3 times v squared into the group to the right. I'm going to reorganize the constants as 3al, then it's going to be v squared times v, so v cubed. Next, it's going to multiply negative u, so it's going to be minus 3al, I'll put u in front because it's a constant, times v squared. Then minus alv cubed all divided by v minus u squared. So that looks quite nasty just to look at because there's so many moving parts going on with this. But there are like terms. 3alv cubed minus 1alv cubed. We can combine our like terms, and that's definitely something. So in the next line, e prime of v is 2alv cubed minus 3aluv squared, all divided by v minus u squared. So thinking in terms of other problems we've solved along these lines, when quotient rule comes up, next step to simplify is usually factor the numerator after you combine your like terms. And this numerator does factor in a nice way. We have al v squared that factors out. I think that's it. But anything you can factor is going to simplify the problem down. So let's take out al v squared. That'll divide out alv squared where the red dot is, just leaving 2v, much easier to look at. Factor out alv squared from this one, and it leaves negative 3u, all divided by v minus u squared. So that's the derivative in its most simplified form. We want to set this equal to 0 and solve it. And this time, there's multiple solutions. We look at how could the numerator ever be 0? And one way is v could be 0, or 2v minus 3u could be 0. A is non-zero, L is non-zero. Those are positive constants. And this is troubling because if you look back on both the second derivative test and the first derivative test, imply there can only be exactly one critical number. So if you have two critical numbers, we need to look into it, which one is going to eliminate and why. And this is the one that eliminates. V is the speed of the fish. If the speed of the fish trying to migrate is 0, that fish has died. Something's gone terribly wrong. Nature is brutal, but we have a way to eliminate that possibility. The fish is not dead. It's greater than u. U is greater than 0. So when this function was written down, it's implied in a lot of different ways. Velocity is strictly positive. So that means the speed of the fish, the velocity of the fish relative to the current could not have been 0. And we go back to that equation. We can solve that equation for v, the variable in the problem, and get the one and only one critical number. We add 3u, divide by 2, and get v equals 3/2 u is the critical number of E. So that's our one and only one critical number. If everything goes right in this problem, that's going to be the value of the velocity of the fish that minimizes its energy expenditure when it migrates a distance L. It says it should be 1.5 times the speed of the current. But we have to really prove that because we know things can go wrong. So now we're going to go to, this was all step 1. Step 2, let's use the first derivative test. So if we can show energy is decreasing to a certain point and then increasing after a certain point, where that point is at the critical number, we have found the absolute minimum. In the first derivative test, we draw a number line down this time. But also this time, velocity is strictly bigger than u. Our number line should start at u, excluding the u value. This is a line for v, the velocity of the fish. And the critical number we found is 3/2 u, which would go here. I'll write it in as a 1.5 u. I think it's a little bit nicer to visualize. Now we look into two test points because there's only one cut on our number line. And so far, this is going out to pretty much the same as every single time we did the first derivative test. We have the derivative here. Here's e prime. What's tricky is we don't know the actual value of u. That's left unspecified in this model. It's meant to be a very general model, which is going to apply to different streams and rivers. But we can still do something, because if this is 1u and this is 1.5u, you could plug in a test point of, say, 1.1u. That would work. You can take 1.1u, plug it in here for v. The rate of change of energy expenditure at 1.1u is plugging in a value for u, exactly where v is, the independent variable. This would be AL, 1.1u squared. We're putting 1.1u right here for v, so that's 2.2u minus 3u all over 1.1u minus u squared. Everything is positive in this numerator and denominator, except for that factor. 2.2u minus 3u is negative, which means the whole thing is negative. We only had to test one value, and this tells us e prime is less than 0 here, which means energy expenditure is decreasing. So if the rate of energy expenditure is decreasing from here to here, we hope that beyond this, it's going to increase as the fish starts swimming too fast. But we just do the same strategy. Take another convenient test point. Say 2u is definitely larger than 1.5u, no matter what u happen to be in this problem. E prime at 2u. We're plugging 2u here in for v, which means everywhere v occurs, plug it in. This is AL 2u squared. 2 times 2u is 4u minus 3 times u all over 2u minus u squared. Now every single factor here this time is positive, including this one. This is the only factor that could flip from positive to negative or vice versa, or come out as 0. That's where we got our critical number, but that's positive as well. So if the derivative is positive at that one point to the right of a critical number where it was 0, it's never 0 again, so it tells us E prime is positive on that whole interval. But that just means energy expenditure is increasing. If the fish goes faster than 1.5 times the speed of the current, then to migrate the entire distance L it has to go, it's going to take more energy. The sweet spot by this model is right exactly at 1.5 U. Is this true in every single fish and stream in biology? Probably not, because things are a little bit more messy when we look at individual species and rivers. There's lots of variation in nature, but this is still a reasonable model, and it gives us a big insight of what the fish are trying to do. So step 3 is going to be our conclusion. It says, determine the value of V that minimizes the energy expenditure. Well, all the first derivative test was doing for us, it was proving we actually do have an absolute minimum. The value of V is already given here, 3 halves or 1.5 times u, the speed of the current. So step 2 tells us we're once again not looking at this picture where energy expenditure, say, always increases or always decreases. It actually turns around from decreasing to increasing, which gives us the absolute minimum. So we can say the absolute minimum of E, you could say here of energy expenditure, but it's defined in the problem. That's what E is meant to be. So you can always use that as a shorthand if you like. We'll go with the shorthand. The absolute minimum of E, energy expenditure of the migrating fish, is at V, the velocity of the fish, which was 1.5 times the speed of the current it's swimming against. So this one was a good choice for first derivative test, only because the very first derivative is very tricky in its own right. Not because the algebra was so messy, but there's a lot of constants going on here as well at the same exact time. Doing a second derivative, that I never tried on this problem. I don't think that's going to be a very fun time. It would just become really messy. And you have to show that your second derivative is always going to be positive to get the absolute minimum. Like we mentioned before, sometimes that's more work than the calculus, depending on how bad the algebra looks for your particular problem. So the first derivative test is nice because even though there's extra steps, building the number line, testing values, if you can compute the first derivative, this can always work as intended. Well, that's our wrap up for this entire section. Again, if you're really curious about how the next problem goes, Snell's law, let me know. It's a good challenge problem to give a try. It involves lots of geometry, lots of clever work with the functions, but there's a path to show how Snell himself came up with these ideas. So this is known as Snell's law, saying the optimal path that light will take is trying to minimize the time it's going to move through a different medium, say like water. Well, Any last questions or thoughts at all, folks, before we call it a night? Okay. Well, this set of problems is going to give you a good guide for when you solve the section 4.7 assignment. The problems that you'll solve there are not all exactly the same, but there's very similar questions in spirit, so you can match up a lot of your problems. Also, don't hesitate to ask about them. Send an email. I'll be happy to help out. And as far as class tomorrow, I'm going to call the campus and see if I can get a classroom. I don't know how long that event was going, but hopefully I won't have to be in the office next time. But have a great night, folks. We'll be back to it tomorrow in section 4.9 next.